I know. This one has memory foam and everything else.
Good. It doesn't really.
Yeah. All right, so we're starting in on this one, 7.58. Now remember, A-Block did a bunch of these, so if there's ones that we don't get to that you really wanted to see, they're probably up in A-Block. They did like 3 of them.
How do we find out?
You go to YouTube, or you go to the site and click on problem set videos. There's a channel for them in YouTube. Okay, so Brittany stands the rest of the skateboard. Combined mass Brittany's skateboard is this. Dave tosses this pumpkin to Brittany and she catches it. And the skateboard is going to roll backwards with the speed of this. So this is a before and after one. All right. So as we look at our setups, we need to use a setup that's before and after. So I'm going to move one up here, and this is what we'll use to do it. Okay. So we're going to need our diagrams in here. So let's see. This was what, 7.58. 7.58. So let's think about some things that we know here in this one. What type of collision is it? Inelastic, right? Or completely inelastic, however you want to say it, right? Someone tell me, how'd they know that? I mean, a lot of people said inelastic. How do you know it's inelastic? Because inelastic, they stick together. Yeah. That's the main way I was telling it. So that's what I would put, here is this is an inelastic collision. My clue was 2 bodies before, 1 after in the system. What do we know about inelastic collisions? Tell me about the momentum. Remains constant. So momentum remains constant in system. Now, folks, this is a great time if you didn't get this problem to actually using your numbers and putting it in and make sure that you get it. So feel free to use the computers, use your phones, do all those type things. All right, that's probably enough for the written part. For the drawings, let's see. Beforehand, I have the girl on the skateboard, and I have the pumpkin. Right, we'll give it a little step. And then during, I still have the girl on the skateboard, but she's kind of joined with the pumpkin. And then afterwards, I have the girl on the skateboard and the pumpkin, all as one body. Don't be intimidated by how well I draw, okay? Remember, your drawings may not look that good. And let's see, stands at rest on the skateboard and gives her inertia. Dave tosses this inertia pumpkin. Brittany, she catches it. She and the skateboard begin to roll backwards with the speed of this. Okay, so she's got no momentum here, but the momentum, the pumpkin has momentum. So I'm going to call that momentum of the pumpkin. And then afterwards, we're going to have momentum in this direction of her, Brittany, and the pumpkin together. So that means while she catches it, there's going to be 2 impulses, right? What do we know about those 2 impulses? Yep. Oh, actually, I could label them J, couldn't I? Not the Jules one, no. Yeah. came in when I tried to call you right afterwards. I did it, and then I changed it first. Because I would say 8, 7, 5. Yeah, 5. So, Brittany, the impulse on Brittany, the impulse on the pumpkin. What do we know about those two impulses? Excellent. They're in opposite directions, and they are equal in magnitude, in size. No, this is the momentum before.
You would say, you would write like on the.
Oh yes, yes, we could do that. I'm sorry, I was going quickly. So the impulse on B due to the pumpkin, and this would be the impulse on the pumpkin due to, what was her name? Brittany? Yeah, so the impulse on Brittany due to the pumpkin, the impulse on the pumpkin due to Brittany. Good point. I was slacking there because there are only two things, so they're acting on each other. But excellent point, though. We should have those. All right, so that would get you full credit on the Y, even if it wasn't drawn as well. And now let's think. Let's use these facts. The momentum of the system is constant, right? So let's grab our equations. And probably need conservation momentum. And so probably need definition of momentum. I'd say that would do it. All right, so, you know, that line in the rubric that says starts with valid physics equations. Well, there are my valid physics equations. Yay, I have that point. So, before I have the momentum, I'm gonna do this very formally. I have the momentum of Brittany and the momentum of the pumpkin. And afterwards, I only have one thing. I have the momentum of Brittany and the pumpkin. Is there one body? And I should have a tick mark on that. Yes? And those two are equal. Annie, you got me? Okay. Are any of those zero, so we don't have to worry about it? This one, right? 0. No worries. So now substituting in, let's see. Both of those are in that direction, right? Do you want to call that direction positive or negative? Positive. I think that's a good choice because then we don't have to deal with negative signs, right? Both momentums are that way. And it's completely up to us which direction we call positive. We're going to call that way positive. Great choice. Momentum of the pumpkin is going to be the inertia of the pumpkin. And the velocity of the pumpkin, which is going to be positive. So I'm just going to put in the speed of the pumpkin. And that's going to equal the inertia of Brittany and the pumpkin. And the speed of Brittany and the pumpkin. Again, it's positive. So we can the momentum equation. I was going to plug in numbers now. I didn't have numbers for the momentum. They told me the inertias and the velocity, so I needed to go until I get those. Okay. So let's see, the inertia of the pumpkin. What did they tell me? 3.7 kilograms. So the inertia of the pumpkin, 3.7 kilograms. Velocity, speed of the pumpkin, I don't know. The inertia of Brittany and the pumpkin together. Brittany's 58, pumpkin's 3.7. So that'd be 58 kilograms plus 3.7 kilograms. Feeling I'm going to run out of room. And then the speed that they move with together, 0.16 meters per second. So 0.16 meters per per second. Oh, good. All numbers except for one variable. Solve for speed of the pumpkin. You guys think you can do that math? Yeah? Good. Excellent. And I think that's all they wanted to know, right? Yeah, in meters per second. Remember, your numbers might be different than my numbers, so make sure you, when you're solving it, you use your numbers, not mine. Check the site. All right, so number 17, or otherwise known as 7.107. So this is 7.107. And we're looking at two rugby player, another rugby player, moving in the opposite direction. Why do they make them leap in the air on this? So they don't have friction. So what are the only parts of this system? The two players. If they were on the ground and they had friction, what else would we have to consider? Yeah, the ground. And maybe the ground would be part of the system then. But by having them jump or putting them on ice or something like that, or a dynamic track, only they are part of the system. So, then, I'll say of all these individual parts, that's cool. Let's see. I'm assuming people had okay finding the initial momentum. Yes. Okay. Yep. So things that I would put here in the Y to cover all of the parts of the problem was, I would show. I'm just going to do it. Show understanding of momentum. And then I would show like I might put something like momentum changes on the individual. How about on the player? On each. Each player due to the other player. But is constant in the system. Just out of curiosity, what type of collision would you call this? Hannah, what type of collision would you call this? Yes, every time I see you texting, I call on you. Question was, what type of collision would you call this? All right, maybe put the texting away and pay attention up here. That might be helpful to you. Anybody else? You have, let me give you a choice, elastic, semi-elastic, and inelastic, and even maybe explosion. What do you think? Inelastic. What was the clue that it was inelastic? That they stick together. All right, good. We're making some progress. All right, so need to do before and after. So I've got rugby player number 1, rugby player number 2. They hit each other. And we have our scrum. And then they stick together afterwards. So let's see. This one had momentum. That way, do they give us numbers or names or anything? Where do I call them? A and B. Okay, so we'll call the green one B, and the blue one A. And then afterwards, which way do you think they're going to move? Oh, they're not. So how much momentum do they have afterwards? Zero. Oh, that's kind of nice. So during the collision, let's see. There's going to have to be an impulse that way on the green guy, and an impulse that way on the blue guy. So that'd be the impulse on A due to B, and this would be the impulse on B due to A. What do we know about those two? Equal but opposite, and they don't cancel out because they're on opposite bodies. Be careful of that. So, we can even put that up here. They have equal but opposite impulses on each. I'd probably get you full credit for your Y. Let's see what they want to know, though. We already said you guys figured out how to solve the impulse, right? The change in momentum. So let's grab an equation for our change in momentum. Huh? Yeah, you would actually need to start with an equation because of our rubric. Because it may not always be that simple. And the equation, the string that you would use, that you'd actually we're only going to use part of, is our impulse string right here. I'm going to make that a little bit smaller. So, and the parts we're going to use here, they want to know the change. What do they want to know? Change in momentum. So we don't need the force right now. We don't need the impulse. We need the change in momentum. Which was changing, the inertia of the body or the velocity of the body? Good. So that's what we're going to use. So the change in momentum is the inertia, which was 92 kilograms. Times the change in velocity. Well, the change in velocity is V final minus V initial. Where did I get 92 kilograms from? Nope. Nope. Well, I asked and people said, no, we know how to do this. We know how to find their momentum. So I flipped. Nope, not at all. Watch what I'm doing. So I put in the inertia, and then the V final is 0 meters per second. The V initial, 7.5. Oh, sorry. I am assuming that we want to talk about this direction being positive. So that would be positive 7.5 meters per second. I should have my little vector symbols up here. And solve for delta P for the change in momentum. Allie, did that answer your question? Okay. I mean, you could. I think what you did is you said this. You said that the change in momentum is momentum final minus momentum initial, and that's how you did it, which is completely legitimate. Also, you can do it both ways, and you'll come out to the same answer. The big mistake I bet some people made was you need to make sure that it's always final minus initial. And here, I don't know, did they mark it wrong if you didn't put negative? Yeah, that's where that negative comes from. Because if you do initial minus final, it stays as positive. And then, we already answered that in our y. Yeah. The initial speed, what was the initial speed of the collision of them before the collision? So for this is where we're going to use the fact that the momentum stays constant in our system. We grab our equation sheet and we grab our conservation in a system. Right? And beforehand, we have the momentum of A plus the momentum of B. Notice my vector symbols equals, what's my momentum afterwards? 0, right? Because they have no momentum afterwards. Do you guys want to deal with the vector nature now? Or let's deal with it as velocity, okay? We'll deal with it after. So this is going to be the inertia of A times the velocity of A plus the inertia of B times the velocity of B equals 0. Should I split that into both sides or substitute index? Substitute in? Substitute in? Okay. So I'm going to substitute in here for this one's 92 kilograms and 7.5, positive 7.5, right? Meters per second, because it was going in that direction, plus the inertia of the B, which was 112, and the velocity of B equals 0. I'm leaving that as a vector for right now. Don't they ask me to find the velocity? The initial speed. Okay, so I'll have to remember if I get a negative that I want the positive of it, right? Because I just want the speed. So I'd bring that stuff over the other side. Could you guys solve that for VB right now, do you think? Answer, please. Yes, no? Yeah? You're going to get a negative answer, right? Does everyone see that you're going to get a negative answer? I'm sensing some of you need me to do the algebra for you. And you're going to get a negative answer, negative something. Well, when I take a negative, when I bring, okay, that's it. Remember your rules of algebra, right? If they're added together, what's the opposite function of addition? Subtraction. So to get this on the other side, I have to subtract that from both sides. When I subtract that from the side with the 0, I get a negative value of it. Kind of think 0 minus 5 is negative 5. And then, so that value is negative. To get the 112 on the other side, I have to use division. And when I divide a negative number by a positive number, I get a negative number. That's what I remember. They asked for speed. So they didn't ask for the vector. They want to know just the value, the speed here, and that will be the absolute value or the positive value of the velocity. All right. save this so I can post